And it's actually recording this time, wonderful. Video 4 is what we're looking at now. Video 4 is about the radius of nuclei and ultimately the radius of individual nucleons. And it's a bit of a weird one, as the last one was, because it's not derived from equations, it's derived from experimental data. So you just need to know how getting that data enabled us to figure out what the relationship was between the radius of the nucleus and the number of nucleons that it contains. So it just says in the spec, R is R0 a to the third derived from experimental data. So let's do that then. There are two graphs. One is complicated and fancy, and the other is simple and boring. We're going to look at the complicated fancy one first of all. So this is what it looks like. Let's see if we can bring it into frame. Wonderful. Ooh, hello. That was nearly disastrous. So there we go. That is the graph that they were able to come up with when they did the experiment for this thing. What they were trying to do was figure out a relationship between the number of nucleons in an atom, which would be A, and the radius of the atom, which would be R. There we are. So we're looking at the relationship between those two. They didn't know. For all they knew, it might well have been that it was a really complicated relationship. Perhaps when you put too many nucleons together, they push each other away more, or they pull each other in more. They weren't quite sure if the density of the nucleus would be affected by the number of nucleons. And it turns out that the relationship is a lot simpler than any of that. The density remains pretty much constant. And really you can figure out the number of nucleons by looking at just how big the nucleus is. So if you think about it, if you were to double the radius of the nucleus, you would expect the nucleus to get twice as wide and twice as deep and twice as tall, so 8 times bigger. And so you would expect it to have 8 times as many nucleons, and it turns out that is exactly what happens. One is the cube of the other. But we usually represent it, instead of one being the cube of the other, we usually represent it with a cube root, because we're interested really in the radius of the orbit rather than A. But yeah, so that's the graph, and we're going to have a quick look at where they actually got this from, because if they were just to plot R against A, they'd have got a curve, and curves aren't all that useful really in physics. Not as useful as straight lines anyway, because there's all kinds of different relationships that can give you a curve, and it's not immediately obvious what kind of relationship you have. Is it cubic? Is it quartic? Is it quadratic? Is it any of these? We just don't know. So what we can do is we can muck about with the axes that we use. So instead of plotting R against A, we can use different things to plot. Hopefully we'll end up with a straight line that we can easily manipulate and work out what's going on. So let's start off then with a graph. We've started off with ln R against ln A. That's really good if you think that one variable is just the power of another. And this is exactly what we found. We found we got a nice straight line. You can see my data points here that I've made up. We got a nice straight line through here, and what they did was they took all these bits of metal foil with different metals, they blasted electron beams at them, and then they looked at how those electron beams diffracted, and from there, with a bit of clever maths, they could figure out how big the size of the nucleus was. And they knew how many nucleons there were because they counted them somehow. Thank you, phone. And so, as a result of that, they ended up with this table of how R changed with A. So they decided to plot a log R against log A graph, and this is exactly what you find. Nice straight line, some sort of intercept that we will call R, call ln R naught, for reasons that will become obvious in a minute, and the gradient was a third. So we know from the straight line relationship y equals mx plus c that if we get a straight line, we can sort of manipulate these terms to work out what y is and what m is and what c is and all that sort of thing. So if I have my y-axis being ln r, which I do, y is the same as ln r, my x-axis is ln a, as you can see, so this m bit, the bit that goes in front of the x, that's in this case going to be a third, and my gradient is a third. So ln r has got to be equal to a third ln a plus the intercept, which in this case is ln r naught. So we get that top equation there. Ln r is a third ln a plus ln r naught. There it is. So then we can do a bit of manipulation. If we know laws of logarithms, which of course we do, we can figure out what's going to go on here. So the first thing I've spotted is that I've got a third at the front of that ln a. What I could do is I could take that third that's multiplying through by the ln a and just stick it as a power of the a. The third ln a is the same as ln a to the third. That's the power thing from logarithms. I now notice that I've got two logs added together. If I've got two logs added together, I can just make that one big log of the two things multiplied. So ln a to the third plus ln r naught is the same as ln a to the third r naught, or ln r naught a to the third. And then you notice that you've got an expression here that's ln of something is ln of something else, so that something must be the same as something else. That's a terrible way of describing it. Get rid of the logs is what we're saying. And what we end up with is r naught a to the third. So just by plotting this graph and getting that straight line, working out the gradient, it was a third, we can figure out that r naught a to the third. And that is how your atomic nucleus radius is dependent on the number of nucleons, which is impressive in and of itself. What does this r naught thing represent? You'll notice, by the way, we called our constant ln r naught so that we could cancel things out here, and we just ended up with r naught here. What is r naught? Well, if I let a to the third be 1, then r naught will just be r. It will be the radius of the nucleus, which means that r naught is the radius of the nucleus when we've got a to the third being 1. If a to the third is 1, then a is 1. So we're talking about the radius when we've got 1 nucleon. So that's what it is. This r naught thing is the radius of 1 nucleon. It's about 1.05 femtometers. You'll remember your femtometers. That's times 10 to the power of minus 15 meters. Pico is minus 12, nano is minus 6, micro is nano is minus 9. Whoops. Let's pretend that didn't happen. Nano is times 10 to the minus 9, micro is times 10 to the minus 6, and milli is times 10 to the minus 3. So glad that was videoed. Yeah, so we've now figured out, just from this graph, by looking at a big nuclei, being able to figure out the radius of an individual nucleon, which is pretty impressive, I think you'll find. So there's your first graph. Your second graph, which we said was simple and boring, is coming up next. Here it is. Boom, there we are. It turns out that, seeing as we've got this relationship, if I was to plot r against a to the third, it would just be a straight line with gradient r naught. That's it really, not the most exciting of things. You can still figure out from this graph, if you were to plot it, that r is going to be proportional to a to the third, and by looking at the gradient you can work out what r naught is, and the sort of relationship comes out like that. It would have been a bit of a punt, I suppose, for them to just draw a graph straight off of r against a to the third. It would have made sense, but usually in general we would plot log-log graphs if we're not quite sure of the relationship and we suspect there's a kind of power relationship between the two. Anyway, there you are. That's how they figured out how big the single nucleon was, and also how they figured out the relationship between r and a, and that is video 4.